Okay, so this is perhaps the last lecture of this introduction and overview topic and first chapter of the textbook. So, in the last lecture, we discussed degrees of freedom of mechanisms, and in this we will discuss within those degrees of freedom um, how much a link can move. So, for example, if a relative motion between one link and another link is possible to the mechanism, then we would explore how far the link can move relative to the other, whether it can move full circle or only part of it. And if it is only part, then how much part, that we will leave for the later discussion on kinematic analysis, because that answering that question would require kinematic analysis. Okay. Yes. So we will discuss mobility. One segment or one aspect of mobility, that is degrees of freedom, we have already studied in the last lecture, and now we will study ranges of motion. Now, this is not so easy to do on a general footing for all mechanisms in one shot. So this depends on case to case, and only for a 4-bar linkage it is possible to do a complete analysis. Otherwise, for every mechanism with dimensions, we need to go deep and do a thorough job, basically, which means a dirty job. So we will not go into that because this is undergraduate course and our discussion is introductory. But for 4-bar linkage, for which the full analysis is possible, we will attempt that. So here we have a 4-bar mechanism in which L1 is the frame, it is a fixed one, fixed link, and then L2, L3, L4. Okay, the other 3 links. Now, this is typically the terminology to denote the 3 moving links. The input link is typically called crank. However, that actually fouls with another meaning of crank. Crank has another meaning, which is a link capable of full rotation. The reason for the mix-up of these 2 meanings, these 2 senses, is that in the beginning, when people wanted to study this area, they felt that if a link is going to operate as the input link, then we might need continuous operation, okay, over several cycles. And the moment the issue of several cycles comes into picture, it was needed that this input link must have full circle rotatability. And that is how the meaning of the word crank as input link and its meaning as link capable of full rotation got a little mixed up. Okay, so sometimes it is used in this sense, sometimes it is in this sense. And when both senses meet, that it is in link, and yes, it is capable of turning full circle, then there is no problem as such. Okay, so follower is actually a very simple thing, which is always the output link. If this is the output, okay, of course, this is the follower. Whether this is output or not, that's a different thing. Now, why I am telling that is that for one kind of tasks, this will be the output. That is, input of this link will be transmitted through some transformation, to this link. Okay, so this will be output link, and from here the purpose of the mechanism will be served. Okay, so that way it is output link. But sometimes you need to accomplish some task for which you need this to be output link. Okay, we will see when we reach the topic of synthesis. But typically, this is the follower. That is, this is a link which can rotate relative to the frame. This is also a link which can rotate relative to the frame. And this is the input. This is driven, and this follows. So that is why this is called the follower. And this is called the coupler, which couples the input link, the driver link, and the follower, that is the driven link. Okay, so this couples them, so that is why this is called the coupler. And now, if this link cannot turn full circle, then what it will do? From one value of the angle to another, it will be able to move, and then for the remaining cycle of operation of this one, it will have to come back. Okay, so this motion, look at my arm, this motion going like this, coming back like this, that is oscillation, that is called rocking, and that is why such a link is called rocker. A link which will rock, which rocks to and fro, which does not have full circle rotatability. And now we will explore the full circle rotatability based on their dimensions. Now, for this link, which is the input link, to have full circle rotatability relative to the frame, it should be possible for it to cross this frame line, line O2O4, at both extremes. At, where is the mouse? Mouse gets lost. Thanks. Yes. So this link for full circle rotatability should be able to cross on this side also, where the point A goes to A1, and it should be able to cross this side also. So from this side to that side, and then that. Okay. Whether you drive it anti-clockwise or clockwise, in both cases, it should be able to cross it both ways. If it can cross one way, it will be able to cross the opposite way also. And now the way the diagram has been made, and this discussion proceeds, the length of the link 1 has been taken as less than length of link 2. That is why on this side the crossing is obvious. Because of L1 being less than L2, the other crossing at A2 is beyond. Okay? If L1 were larger, then A2 would fall on this side, and analysis would go in a different order. Okay. Finally, the result would be same. It may be a good idea to do that exercise on your own and check that similar situations you get. Actually, while making this entire document, entire notes, I did that one more round and figured out how that would lead to the same results in a different order. Okay. So input link 2 can rotate full circle if it can cross the frame line at both extremes. At the left extreme, A1, and at the right extreme at A2. Fine. Now, when does it succeed in crossing? When, if A comes to A1 or A2, in both cases, the links don't break. Okay. So for not breaking, what is needed? L1 and L2 align L1 and L1 L2 align along a line, and the other two, L4 and L3, they together should form a triangle, a valid triangle. So that means the triangles that we are looking for, which should be possible, are O4, A1, B1, and similarly O4, A2, and B2. So this is L3, this is L4, this is L3, this is L4. Okay. These two triangles should be possible. That means they should not violate the basic necessity for triangle formation, that the sum of two sides should be larger than the third. Now in this case, this is one side already formed, L1 plus L2. The other two, L3 plus L4, should be larger than this O4A1. Okay. L1 plus L2 should be smaller than L3 plus L4. This is the requirement of closure of this triangle at the left extreme, A1. When A goes to this extreme, A2, then O4 A2, this side is L2 minus L1. Now, this is the point, this is the step which is utilizing this. Okay. Otherwise, it would have been L1 minus L2. So, in that case, for that, we don't know a priori which is the larger link, L3 or L4. The way I have made this construction, L3 is longer, so L3 is leaning this way, and L4 is shorter. But we have not talked of data. So L3 plus this should be larger than L4, and L4 plus this also should be larger than L3. So that is this. L3 plus this one, O4A2, is larger than L4, and L4 plus O4A2 is larger than L3. Now these three we will reorganize here. This one is straightforward. It has come as it is. For this one, we take this L1 on the other side. So L1 plus L4 is smaller than L2 plus L3. And here also L1 we will take on the other side. And so L1 plus L3 is smaller than L2 plus L4. Now you know, all these three together, what do they really mean? They mean something very interesting. They mean that L1, for that condition to hold, L1 should be smaller than each and every link. Okay. So we started with L1 being smaller than L2. But if L2 is capable of crossing both sides, then L1 should be smaller than each of the three. Those three I have reproduced here. Now, how do we say that L1 should be smaller than each of the three? You see, if you add first two, then on the lesser side, left side, what you will get? Twice L1 plus L2 plus L3. On the higher side, both higher, what you will get? L2 you will get, L3 you will get, which is there on the other side also. Apart from that, you will get 2 L4. So L2 and L3, from both sides you will cancel. On this side it will be twice L1, on this side it will be twice L4. So that means L1 is less than L4. If you add these two similarly, then you see L3 and L4, L4 and L3 will go off, and what will remain? On this side twice L1, on this side twice L2. So this shows that L1 is less than L2 also, which anyway we knew from the beginning. If you add this and this, then you see L2 and L4 will be common on both sides. L4, L2. What else? On the left side, smaller side, you will have twice L1. On the higher side, you will have twice L3. That means L1 is less than L3 also. So that means essentially this. Okay. Or in other words, L1 is the shortest link. Call it S. And if L is the longest of these four, which basically means now that longest of L2, L3, L4, if you denote by L, the longest one, the way you denoted the shortest one by S, then this condition would require L plus longest is less than the sum of the other two. Why? Because, sorry, S plus longest. S plus longest. Because you see S is L1, so S plus L2 is less than the sum of the other two. S plus L3 is less than the sum of the other two. S plus L4 is also less than sum of the other two. That means S plus any one of them is less than the sum of the other two. So in one shot, you can say S plus the longest, because if the longest sitting there holds, then the shorter ones will certainly hold. Okay, this is the condition. That is, shortest plus longest should be less than the sum of the two intermediate ones. Okay, and this is the famous Brashov's criterion for full circle rotatability. That is this. That is full circle rotatability between the shortest link and its adjacent. And those four-bar mechanisms which satisfy this requirement, they are called Brashov's linkage. Now consider the inversions. If you fix the shortest one, the way we have done in this particular case, you get a double crank. Now you see, the way the word crank is being used here, it is not used as input link, it is used for full circle rotatability. Okay. Now, why do we say double crank? Till now we know that only L2 can rotate full circle relative to L1, and we have checked. You see, if in these three lines, if in these three inequalities, you interchange L2 and L4, nothing changes. Because this one anyway remains as it is if you interchange L2 and L4. In this, if you interchange L2 and L4, then in this place you will get this. And here, as you change that, in this place you will get this. So these same three things you will get for the condition of full circle rotatability of L4 relative to L1. Okay. So that means under the same conditions, not only L2 but L4 also can rotate full circle if the shortest one is fixed. Okay, that is why it is called double crank. You can drive it by driving 2, giving input to 2, link 2, or to link 4. Okay, and if you give input to link 2, then as link 2 completes full circle, link 4 also will complete full circle. Okay, of course, at a variable rate. If link 2 moves uniformly, link 4 will take different amount of time in completing different parts of the cycle. Okay. In the second inversion, in fact, two inversions appear here together. If you fix a link adjacent to the smallest one, then it is crank rocker. Why? The argument is very simple, straightforward. It cashes on the idea of the inversion. In the inversion that we have discussed, link 1 is fixed and 2 is rotating full circle relative to 1. Now, the same motion can be considered as if link 2 is fixed, and in that case, from the perspective of link 2, you will find link 1 moving full circle. Okay, so it is actually relative motion, so it is the same thing. So relative to link 2, 1 can move full circle. So if 2 is the frame, then link 1 will be able to move full circle, not link 3. Okay, and in fact, in this case, if you fix the shortest one, then not only 2 and 4 move full circle, I mean rotate completely, even 3 spins completely 360 degree on its own. Of course, you cannot say full circle rotatability because the motion of link 3, the coupler, is not circular the way the motion of 2 and 4 are, because one point of 2 and one point of 4 are fixed. Link 3 is free, so it doesn't have a fixed point. So the motion of the coupler is not a proper rotation. It's a rotation translation combined. It's a funny floating kind of motion. But its line AB, what is the line angle of the vector from A to B relative to the frame line, that is the vector from O2 to O4. If you see that, whether it can acquire every value from 0 degree to 360 degree to one circle, one cycle of operation, so that you can check, and you will find that in the case of double crank, it is actually triple crank in the sense that link 3 also turns complete. And the textbook shows you one very interesting extension by which that gets proved in a very clever way. Okay. So I suggest that you look at it. I did not bring that into this discussion because it's a little sideways and not germane to our main issue. Okay. If the link adjacent to S is fixed, that is smallest link is fixed, then you get crank rocker. That is, the smallest one can rotate full circle relative to that. Okay, fixed one, now fixed one, and the other one will be rocker. That will not be able to turn full circle. Why? You can get that very easily because look at the figure. If you fix link 2, okay, and you ask for full circle rotatability of link 1 that you are getting, because relative to link 1 you got full circle rotatability of link 2. Now with link 2 fixed, if you are looking for full circle rotatability of link 3, that means you are looking for the full circle motion of this link relative to this, not relative to link 1, relative to 2. Now for that, you need this angle to be larger, larger, larger and go beyond 180 degree. Okay. And if uh, if this is the shortest, okay, then that will not be possible. Why? Because when this angle becomes 180 degree, then these two go in one line, okay, long, 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 okay, and this is shortest. We know that even if this is the longest link, the Grashof condition has clearly told us that shortest plus longest will be smaller than the sum of the other two. Okay, so if this angle tries to go larger, 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 and approaches 180 degree, then these two, even by straightening, they will not be able to complete that. Okay, so that triangle will never close. This triangle O2, O4B with O2AB aligned will not be possible. Similarly, from this side, if you so this is going to be rocker. Okay, if you fix this, that is smallest fixed, it's double crank, in fact triple crank, and adjacent to smallest fixed, whether L2 or L4, in both cases it will be crank rocker. The smallest one will be the crank, and the other side will be only rocker. And then if you fix this, then what will happen? If you fix this, then both will be rocker, this side as well as this side, because if link 3 could not move full circle relative to 2, then the link 2 also cannot move full circle relative to 3, and same thing on this side also between link 3 and 4. However, interestingly, it is possible that with link 3 fixed, this link can spin completely. Okay, because with this link fixed, this one was able to spin completely, as the textbook's extension will show you. So with link 3 fixed, this will be able to spin completely. But that is not of great significance, that is not of great utility. Because if the coupler spins completely, I mean, how do you utilize that? You wanted a link adjacent to the frame to be full circle rotatable. Okay, which you could use as the crank, the input link for continuous motion. Okay. So in this case, it will be double rocker. That doesn't mean that it is a useless mechanism. If the mechanism really needs only partial motion, not full circle motion, or if you have some other auxiliary means to give input to this, for example, this could be the output link of another 4-bar mechanism, which is crank rocker. So through that, you might be able to give input to this, and this is rocker, and that transforms the motion to another rocker. That is possible. So double rocker mechanisms may have some utility in certain situations, and that will be what you will get if you fix this in a Grashof linkage. So that means in Grashof linkage, you have double crank, crank rocker, double rocker, all cases. And these are 4 inversions. If you fix the smallest, then you get cranks on both sides. If you fix adjacent to the smallest, either this one or that one, then you get crank rocker. The smallest is the crank, the other one is the rocker. And if you fix the link opposite to the smallest, then you get double rocker. And in the non-Grashof linkage, for which the longest plus shortest is actually larger than the sum of the other two, in that case, you will get always double rocker. Because this Grashof's criterion we got as a condition for full circle rotatability. So if that condition doesn't hold, then the full circle rotatability will not be there. Now you will say that what if they are equal? For example, this is 3, this is 7, and this is 4, this is 6. So 10 and 10. Okay. So in that case, all inversions would give you situations like Grashof's linkage, except that there will be collinear link uncertainty configuration. Because if pairwise they give you equal sums, then there will be some configuration in which the longest and shortest will be along one line, and in that configuration, the other two also will be forced to be along the same line because they are actually trying to close the triangle. Okay, so the base of the triangle is L plus S, and the other two sides P and Q, and between them the angle is 180 degree. Okay, so all the 4 links will get aligned along the same line. Okay, and such situations might come twice in a cycle, once this side and once that side. So these are some, the way you call these as the Grashof linkage, these as a non-Grashof linkage. Sometimes some people might say that these are changeover linkages. Why changeover? Because at the configuration, which is actually uncertainty configuration, in which everything gets linear, everything gets aligned, then as you continue beyond that, then some of the links, whether they will continue in the configuration in which they were earlier operating, they might change over the branch and cross over to the other branch. And what is this idea of branch? When two links, one link has its say one link has its fixed point, located point here, another link has its located point here. Between the two links there is a dyad. So the dyad might get a configuration like this, a configuration like this, up and down, say elbow up and elbow down. Okay. But if the angle at the elbow is 180°, then the up and down merge at the same thing. And then as you cross over, okay, so crossover mechanism, crossover linkage. So as you cross over, beyond that, then something which was going this way and crossing, after the alignment, it might as well come back rather than crossing. And that is quite possible. Okay. So that is the kind of uncertainty configuration that you get with links linear, and that is why the branches can cross over. From the elbow up configuration, it can go to the elbow down configuration. Now, this is full circle rotatability conditions, the full set of conditions for 4-bar linkage ordinary. That is 4R. All the angles are, all the points are, all the pairs are revolute pairs. Now, what about 3R1P? That you get as a corollary of this criterion by considering that a prismatic pair is after all a revolute pair with the links of infinite length. Okay. So this 3R1P mechanism, okay, can be considered as a 4R mechanism with this link being so long that the fixed pivot is at an infinite distance. And therefore, the poor fellow L1 will also have to be considered that long, almost that long, and go and meet it at that O4 somewhere. Okay. This we have seen earlier in one of the lectures. So two of the links are infinite. Are they equal? Not really. The way I have made it, they are not equal. L4 is slightly longer than L1. You see, the difference of two infinities can be almost anything. Okay. In this case, the difference of these two infinities, L1 and L4, is actually E. Because from here, in this direction, you get it at a very large distance. And from here, in the same direction, again at a very large distance, you get that point. Okay. Point at infinity is at the same, the point of intersection has to be at the same direction. You cannot say that this will be somewhat angular, somewhat inclined, nothing of that sort. Because if it has to go only 7 kilometers, then it will be an angle. If it has to go 70 kilometers, then also it will be angle. Okay. But if it has to go indefinitely, then both will be in the same directions. Both will be parallel. So you say parallel lines meet at infinity. Okay. So then the distance, the two distances, the two lengths will have a clear difference of E. Okay. So the two of the link lengths are infinite. In this case, L4 is slightly longer. Difference is E. If this line of sliding were below this point, this fixed pivot, then L1 would be longer. Okay. So the other two are of finite length. So between these two, one of them has to be smaller. So whichever is the smaller, that will turn out to be the shortest link, say L min. And other one of these two you call as L prime. Similarly, between these two, one of them is the largest, in this case L4, in this particular figure, L4. So call that L max. And the other one, in this case L1, that will be the other, that you denote as L double prime. Now the Bishop's criterion, shortest plus longest is less than the sum of the other two. That will be L min plus L max less than L prime plus L double prime. Now what you do, L double prime is the smaller of the two infinite links. Take it on the other side. Now you have got here L max minus L double prime. We don't know how big is this. We don't know how big is this. Both are indefinitely big. But we know their difference. And now the condition for full circle rotatability will be this. L min plus E is less than L prime. That means out of these two, whichever is the smaller, plus this eccentricity or offset should be smaller than the other finite ring length. Now, if L2 is smaller, then which case you have got? You see, in this case, the fixed link is actually L1, which is a large ring. Okay, cannot be the smallest. So you have got only these two as candidates. If L2 is smaller, then you have got the frame is adjacent to the smallest link. Okay, in that case, you are getting crank rocker. So it is a case of link adjacent to S fixed, hence crank rocker. In this case, crank rocker means that this L2 can rotate full circle, and this fellow would be able to now this fellow. What is this fellow? This fellow is the link of the infinite link, which about the infinitely away point will only rock. It cannot go full circle, obviously. And in practical terms, this slider will go back and forth. Okay. Prismatic pairs always have to have joint limits. Okay. In this case, the joint limits are geometric. So as this goes full circle, it can because it is the crank, as we have just now seen. So this comes leftmost and then goes rightmost, then leftmost, rightmost, and that one oscillation takes place in one cycle of motion of the crank. Okay. In this case, L2 goes full circle, L4 to and fro. This is the useful slider crank mechanism. This is a slider and this is the crank. In both cases, it is a crank, input link or full circle rotatability. Of course, it will not be the input link if this is the one which is really driving. But anyway, so it is full circle rotatable, so it is crank. In an engine, this is the engine mechanism. In an engine, actually, if the frame is the cylinder and the crank pivot also. Okay, and in the cylinder, slider is the piston, so that is actually the input link. And as that goes back and forth, this rotates completely and continuously, cycle after cycle, cycle after cycle, sometimes at 3000 RPM. Okay, because turning the wheel is a way of power generation in our civilization. If it is the other way around, if L3 is smaller, if L3 is smaller than L2, then it is smaller than everything else because other two are infinite length. Then you know what is the case. L3 is the smallest link and the frame is the link opposite to the smallest link. Okay? If L3 is smallest, it is a case of link opposite S fixed, and that means double rockers. And in that case, this also cannot rotate full circle. So this can only rock and this can only slide back and forth, which is in a way equivalent to rocking. So in this case, L2 rotates to and fro, L4 slides to and fro. Okay. So this is the corollary of the Grashoff's condition for the side effect. So I think this completes the discussion on range of motion. I mean, that much discussion which can be done in this classroom. Okay, and the corresponding assignment problem actually tries to bring out the implications of the conditions, clash of conditions, and some of the kinds of linkages that we have discussed in this in proper light. Okay, so thank you. So in the next lecture, we will move on to perhaps the most important topic of this course, which is kinematic analysis.